Hi all. In this video, we see some of the computational techniques for modeling multiphase flows. So, what is multiphase flow? So, we know that there are different phases like solid, liquid, and gas. So, any fluid system consisting of two or more distinct phases flowing simultaneously in a mixture form and also having some level of phase separation at a scale well above the molecular level. So, a fluid system having more than two phases and flowing simultaneously in a mixture form, and the phase separations are at a scale above the molecular level are defined to be as a multiphase flows. And these multiphase flows can be classified based on what phases involved in the fluid flow systems. For example, gas solid flows, liquid solid flows, and gas liquid flows, liquid liquid flows, and gas liquid solid flows. So the first type, the gas particle flows. So in this and the solid particles involved in motions which are suspended in the gaseous phase. These solid particles constitute a dispersed phase, whereas the primary phase, is termed to be as a continuous phase. And again, based on the particle density, the number of particles involved in the fluid flow, they can be classified as a dilute flow or a dense flow. In a dilute flow, mostly the particles are very less in numbers, and the motion of the particles are mainly governed by the way the gas impacting forces through surface and body forces on them. Whereas in dense phase flow, where the particle density become high, there will be some interactions between particle, and that govern part of the solid particles motions. Moreover, the solid part and the gas particle flow also can be classified based on the bounded domains in a free surface, unbounded domain, or it's a bounded domain. For example, in a bounded domain like there would be some kind of interaction between the solid particles with the boundary walls. So these things will be detailed and studied in a separate videos. How this gas particle flows, how to formulate the flow multiforce. I'm just giving an overview of what does mean by gas particle flows. So again, it comes to the case of liquid solid flow. There are two phases like liquid and solid. Here, there will be some suspended motion of solid particles in the liquid phase, and the solid particles will be as a dispersed phase, and the liquid will be as a continuous phase. And again, based on the particle density, it can be classified as a dilute flow or dense flows. And unlike the gas solid flows, here the liquid solid flows have density are nearly same. So the main factor governing this mixture of flow is the pressure gradient between the inlet and the outlet. Here, this is a very interesting flow phenomena happens during gas liquid flows. There are many different configurations, unlike gas solid flow or liquid solid flows. Here, there are mainly three different kind of configurations happen. One is dispersed flows, or separated flows, or a mixture flows. Then dispersed flows, what is a dispersed phase, what is a continuous phase? For example, in a bubbly flow, bubbles will becomes a dispersed phase, gas will be a dispersed phase, and liquid will be a continuous phase. In a droplet flows, liquid will be a dispersed phase and gas will be in a continuous phase. And in terms of some kind of well separated flows, where there will be a clear distinction between the liquid and gas, like in flow in the ocean, some kind some kind of weather atmospheric flows, there will be a massive scale difference between the two phases. And there are other third category called transition flows, and which is very interesting, especially application to the process engineering. And that can be called as a slug flow, where a, it's not like a dispersed bubbles, it's a huge slug of gas packets flow along with the liquid continuous phase. And there can be some kind of bubbly annular flows where only the bubbles formed only in an annular film region, and the center will be a gas core. And here the center gas core will be filled with droplets, and here there will be a center gas filled with droplets and also an annular film filled with gases. So there are different configurations. Even there will be a flow transitions while the external conditions differ during some chemical processing industries. So there are many applications of multi-phase flows. Almost all those fluid flows involved in all around us are involved in one or the other way of multi-phase flows. For example, gas solid flows, it sandstorms, volcanoes, dust collector, fluid icebergs are very important applications, and rocket propellants, uh, and spray drying, spray castings, all belong to gas solid flow. And liquid solid flow, and there will be a natural phenomena happening in the environmental flows in rivers, sea, soil erosions, iceberg formations, blood flow, non-Newtonian blood flow, industrial slurry transportations, water jet cutting, sewage treatment plants, and gas liquid flows, again portion flows where there is a separated flows. Again, if there is some kind of aerosols where it's kind of dispersed flows. And in nuclear reactors, internal combustion engine, liquid propellant rockets, and liquid flows like emulsifiers, fuel systems, and where three phases involve, like airlift pumps from the groundwater and fluid icebergs. There are many important applications involving multi-phase flows. It's very crucial to understand how the flows happening when two or more phases involved, and how to model them and make it as a design tool. So, coming to the single phase flows, as we use the concept of continuum mechanics and derive equations, governing equations like Navier-Stokes equations based on conservation laws of mass, momentum, and energy. Along with that governing equations, we also have some constitutional relationship based on thermodynamic state and energy transfer. And we close those Navier-Stokes equations where there is a strength-strain relationship with viscosity and heat diffusion coefficients. But unlike the single phase flows, deriving the flow modeling for multi-phase flows is really a tedious task because of certain complexities involved, like presence of multiple deformable moving phase interfaces between these interfaces between the phases involved. And there will be a significant discontinuities of the fluid properties along those interfaces, like gas, solid flows. And the flow characteristic, there will be some kind of there won't be a single flow characteristic, there will be a several flow characteristic, depends upon the external conditions. So considering all these things, it will be a very tedious way in comparison to a modeling of a single phase flows. So how do we develop those mathematical models? So from those concept and the foundation concept of governing equations of single phase flow, like conservation of mass, momentum, energy, we may use of macroscopic averaging process, which we will be detailing in same like what we did in continuum mechanics, like averaging technique. We try to model and simplify it for a greater computational efficiency, to consider those separated phases as a continuum fluid on on all the phases, and those that simultaneous flow will have some kind of an interacting between these phases, that appearance of the terms will be modeled through some kind of qualitative understandings from the direct numerical simulations and log eddy simulations. So here we don't use at all occasions DNS or large eddy simulations, but those will be used as a simulation tool or a research tool to formulate these multi-phase flow models using averaging techniques. The reason is all those resolutions or the micro evolutions of the interfaces are not necessary in a in an engineering applications. So these resultant equations by this averaging process and closing through this DNS and LES resembles similar to kind of a single phase flows of uh, field equations, field equations like single phase flows, but they will have some extra terms that I mentioned earlier. They will have some interface coupling, exchanging mass, momentum, and energies. So those interface, those additional terms has to be close similar to that of a single phase constitutional relations. So that way the constitution relationship emerging from those averaging process differ from the way the phases are involved and the way the interactions are involved, and that is the main difference between how the equations are formulated based on the classifications of multiphase. Like the example, gas particle flows have different flows of formulation compared to the liquid liquid flows or gas liquid flows. However, there are some techniques which were existed during the single phase flow, like turbulence modeling, K epsilon turbulence model, K omega turbulence models. The two equations model are similar kind of logical techniques also being utilized here to formulate multi-phase flow modeling and try to make some closer models for the multi-phase flow models. And also while doing, when we are solving some computational techniques, like there are these interaction terms of nonlinear interactions that has to be handled properly in order to make a stable solutions, computational numerical solutions. And these some of the numerical techniques that we adapted in single phase flows for handling the nonlinear terms, like partial elimination algorithm or sense algorithms, are also somehow it is been tailored for the calculations of the multiphase flows. And again, we know that in solving a Navier-Stokes equation, there will be a strong pressure velocity coupling, and those terms has to be handled properly, like using a simple algorithm. Similar kind of ideas have been borrowed in multi-phase flows, and they develop an algorithm called IPSA, interface slip algorithms, and that also will be covering how these algorithms are modulated and formulated, and how can the computational procedure can be in future videos. And moreover, there are other terms applied in the physics, like population balance approach, also been utilized in gas liquid flows. This I'm giving some kind of an examples, and there are also some kind of other techniques are utilized in uh, um, gas solid flows, how that solid equations are formulated from Newton law of mechanics, and how when the solid particle pass through computational cell or finite volume, how those that will be interaction with the gaseous phase, whether it will be an one-way coupling or two-way coupling. So those modeling techniques also have somehow we borrowed from some single phase techniques. And there are also some explicitly formulations for a multi-phase flow, like volume of fluid method, um, interface tracking method, level set method. So those all those computational techniques all will be covered in the forthcoming videos. And also how, in addition, the complications involved when these multi-phase flows become more into a turbulent nature. So on forthcoming videos, we will be covering one by one. classifications. But first we will be covering gas particle flows, then we will covering liquid solid flow, then liquid flow has a wide variety of configurations, and all together how this all these have some kind of a common modeling techniques. All will be covered in detail in forthcoming videos. Hopefully we'll see and study through all these multi-phase flow modeling techniques, which are very important for the industrial applications. And I would like to thank the author of the book called Computational Techniques for Multi-Phase Flows. And this is the reference that this lecture is inspired from. Thank you very much.